In this module, you will learn to define the axiomatic approach to probability. You will also learn to prove basic theorems related to probability. We know that an event is an outcome or a collection of outcomes. But how can you quantify the chances of an event happening? Mathematicians attempted to measure the happenings of an event using probability theorems. We know the classical theory and the statistical theory of probability. In the classical theory of probability, the probability of an event is equal to the number of outcomes favorable to the event divided by the total number of possible outcomes. In this theory, the number of outcomes is finite and all the outcomes are equally likely. However, in the statistical theory of probability, we find the probability of an event happening based on the observations and the data collected. Neither theory can be applied to experiments that have an infinite number of outcomes. Furthermore, in the classical as well as the statistical theory, it is assumed that all the outcomes are equally likely. That is, the outcomes are equally probable. This is logically incorrect. For example, the event of getting at least a head in an experiment of tossing of two coins simultaneously. Therefore, A.N. Kolmogorov, a Russian mathematician, developed a new theory of probability in 1933. This is called the axiomatic approach to probability. In this approach, some axioms or rules are laid down to interpret probability. Let S be the sample space of a random experiment. According to the axiomatic approach to probability, the probability P is a real valued function whose domain is the set of all the subsets of sample space S, and the range is the interval 0, 1. Here function P satisfies some axioms. Let's take a look at them. The probability of any event, say A, is non-negative, that is, P of A is greater than or equal to 0. The probability of the sample space S is 1, that is, P of S is equal to 1. If A and B are mutually exclusive events, then P of A union B is equal to P of A plus P of B. Let's consider an experiment where a die is rolled. The sample space associated with this experiment is shown. Thus, the probability of the event getting 1 is 1/6. The probability of the event getting 2 is 1/6, and so on. In all the cases, we notice that the probabilities of the events are equal, which is 1/6. We also notice that the probability of each event lies between 0 and 1. Hence, the probabilities of the events satisfy axiom 1. Now, let's add the probabilities of all the events, which is equal to 1. This implies that the probability of S is equal to 1. Hence, the probabilities of the sample space satisfy axiom 2. Now, let's consider a coin is tossed once. The coin has 3 times the chance of falling heads up as it has of falling tails up. Therefore, P of H is equal to 3/4, and P of T is equal to 1/4. The values of the probabilities lie between 0 and 1. On adding the probabilities, we get 1, which is the probability of the sample space. Now, we'll prove some theorems related to probability. Let's begin with the theorem which states the probability of an event that cannot occur is 0. That is, P of phi is equal to 0. Consider two events A and B such that both A and B are null sets. Thus, A intersection B is equal to phi. This implies that events A and B are mutually exclusive. Hence, P of A union B is equal to P of A plus P of B. This implies P of phi union phi is equal to P of phi plus P of phi. On simplification, we get P of phi is equal to 0. Hence, the probability of an event that cannot occur is 0. The next theorem states that if A is an event in sample space S, then 0 is less than or equal to P of A is less than or equal to 1. Given that A is an event in sample space S, we know that phi is a subset of any event. Thus, phi is a subset of A, which is a subset of S. Therefore, P of phi is less than or equal to P of A, which is less than or equal to P of S. We know that the probability of a null set is 0 and the probability of a sample space is 1. Hence, the probability of an event of a sample space always lies between 0 and 1. Let's prove a theorem on the probabilities of equally likely outcomes. If E is an event in a sample space S containing n sample points that are equally likely, then P of E is equal to 1 divided by n. Let P of E be x. Consider that E1, E2, E3 and so on are the elementary events that contain each sample point in sample space S. Thus, the events are mutually exclusive and exhaustive. Therefore, the union of the events is equal to S. The probability of the union of all the elementary events is equal to the probability of the sample space. It implies that the sum of the probabilities of all the elementary events of S is equal to the probability of the sample space. Since sample space S contains equally likely sample points, the probability of each event containing a sample point will be x. Thus, we get sum of n number of x's is equal to 1. That is, nx is equal to 1. Therefore, x is equal to 1 divided by n. Hence, P of E is equal to 1 divided by n. S is a sample space containing n sample points, and A is an event in S containing m sample points. If each outcome is equally likely, then P of A is equal to m divided by n. Let E1, E2, E3 and so on be the elementary events of S containing each of the m sample points of event A. We know that the events are mutually exclusive and exhaustive. Therefore, the union of all elementary events of event A is equal to A. The probability of the union of all elementary events of A is equal to the probability of event A. This implies the probability of A is equal to the sum of the probabilities of each of the elementary events of A. Since we know that S contains n sample points, the probability of each of its sample points is equal to 1 divided by n. Therefore, the probability of event A is equal to m divided by n.